My name is Jason Kosmatka. I'm a project manager with AE2S, and this big long title I'm going to be talking about is highest priorities: no more taste and odor complaints, implementing strategies to address algal toxins for the City of Fairmont, Minnesota. Presentation topics: planning. How did we get to where we are now? All the steps that we took. The taste and odor pilot study was one of the main steps that we used to figure out the appropriate technology and treatment processes to eliminate all the taste and odor compounds. I'm going to talk a little bit about construction, the startup, some of the lessons we learned in startup, and also the results that we saw with the new treatment system. The Fairmont Water Treatment Plant serves a population of 10,500 residents. It was originally built in 1926, expanded in 1961 to 4.5 MGD, and the new water treatment plant is a 5.4 MGD Class A lime softening plant with filtration. It's a little bit hard to see up here, but right here is a brand new water treatment plant. Kitty corner from it is an old plant, and that's our source water, Bud Lake. There's actually 3 pipes going out into Bud Lakes where we were just right across from there. Oh, and a little bit about trying to treat the source water. This old water treatment plant, they tried to treat the lake. They had, I believe, 4 or 5 solar bees out there. They used PAC, they used a micro strainer for algae removal. They had chlorine dioxide to try to keep their disinfection byproducts in place, but none of these really worked, and in the summertime, their taste and odor was quite up there. Facility planning step. Basically, source water evaluation. There is a pretty large aquifer over there, but all of us know in southwest Minnesota, the water's pretty hard to deal with, but one of the biggest ways to get rid of the cyanotoxins, the taste and odor compounds from algae, is to use groundwater. But you can see the groundwater here has 800 parts of hardness, 1,000 parts of TDS, 573 sulfates, which are way above the SMCLs, and the gross alpha is actually above the SMCL, or the MCL, which is, I believe, 15 picocuries per liter. But they did have sufficient quantity. Bud Lake, they had sufficient quantity and quality, and they also had a lot of operator experience. They've been treating Bud Lake surface water for, well, since the original plant was built. But taste and odor, and we can deal with taste and odor. Those things right there are very hard to treat, very hard to deal with. And as water professionals, all of us know, if we send out a water to residents who aren't used to it, that have a TDS of 1,000 and sulfates of 750 or 570, we're going to need some of that in town. So because of that, we decided that Bud Lake was the way to go. Treatment target goals. Since we're treating Bud Lake, some of the, obviously algae removal is one of the biggest items. Softening from Bud Lake. Bud Lake has a hardness of about 200, so it's right at the cusp of do we need to soften, do we not need to soften. They've been softening since 1961. The residents are used to a soft water, so the city decided that that is one of the requirements of the new plant was softening. All these other things are common to any water treatment plant. 2 of the main things that we identified early on was that they wanted a multi-barrier treatment approach, so multiple steps to eliminate all the taste and odor constituents, and also taste and odor control. We can produce a water that meets every single criteria, meets all the requirements of the Surface Water Act and all that stuff, but if it doesn't taste good or smell good, the consumers aren't going to drink it. And they're going to be buying a lot of Culligan water, which advertises a lot in Fairmont, or used to, I don't know if it does anymore. Through our taste and odor, basically a pilot, blue-green algae, which is also known as Cyanobacteria, was the main cause of our taste and odor compound. Cyanobacteria produces MIB in geosmin, which is always, as we know, related to the musty, earthy smell. The MIB in geosmin is not regulated, but we also had the presence of cyanotoxins, and the 2 of the main algae species that we had out there, besides the blue-green algae, were Microcystis and slender, I'm not going to pronounce that one, but that one over there. And those ones cause your Microcystin LR and other cyanotoxins, which are currently on the EPA contaminant candidate list, and that's something else that we're going to look at to make sure that we can treat down to acceptable levels. A little bit about cellular constituents. So basically we have our blue-green algae, and it's sitting there, and inside of the cell wall is our MIB, geosmin, other cyanotoxins, and our taste and odor causing compounds. Once the cell lyses, or lysis occurs, the cell wall bursts and releases all them taste and odor compounds into the water, and that's what the residents are actually drinking, are the MIB and geosmin that have been released into the distribution system. So during the facility plan and our taste and odor pilot study, we were waiting for a taste and odor event, and in June it happened to us. So when the plant operators told us that we had an algae bloom, we went out, but operators went out to the lake, took some samples at different depth throughout the lake. The lake is a shallow lake, about maximum depth of about 20 feet, and during times of the summer, it looks like you just about walk on it, it's so green. But they took some samples at the lake surface. They had geosmin of 16,000 nanograms per liter. At the intake level, which is 16 to 20 feet down, is between 70 and 80. And the odor threshold is commonly around 30. That's when the common person can taste and smell geosmin. For MIB, it's about 10 micrograms per liter, but that we didn't really have as much MIB as we did geosmin. Same thing with microcystin. That was present there at the surface, 160, intake level 0.5. It was still of concern because the potential regulated threshold might be down to 0.1, so something that we still might have to lower in our treatment plant design. Now, if you notice that the surface has, infinitely more amount of MIB, geosmin, and microcystin at the surface than it does at the intake level. That's basically because when we took these samples, we took them during the middle of the day, and cyanobacteria, which is like an algae, it wants to swim and rise to the surface and use the sun basically for photosynthesis or as an energy source, and it's up at the surface instead of way below. During the dark hours, nighttime, that algae is going to sink, and we'll see that in lagoons also, but it'll sink down to the middle of the lake stratum or down to the bottom. So actually, when you're on a 24/7 operation, if you're drawing in water at night, you're probably getting a lot more of this, the cyanobacteria coming into your plant than you are during the day. So that's maybe one thing you can look at about taking in water if you're not operating 24/7. We knew we were doing a new conventional lime softening water treatment facility, but what we didn't know and we needed to figure out is algae removal. How are we removing those full algae cells, the cells that are nice and still viable? Dissolved air flotation was one of the things we looked at. Like I said, algae likes to float. You bubble some air through it, use a little polymer, scrape it off the top, and places in Florida use that all the time for just algae harvesting. And then what are we using for our taste and odor control? There's quite a few methods that we could do for that. We had a pilot study where we were able to pilot several different technologies. DAF was one of the items we piloted. Membranes we did not pilot, and that was removed from consideration pretty early on because of cost, membrane fouling, the high loading we'd have on there, and cost. So we removed membranes early on. Ozone we looked at, UV peroxide, and granular activated carbon. And basically we had a skid there, we piloted all the chemicals, piloted all the technologies, tweaked the chemical feeds, and operated it for a while till we had steady state. And then once we knew everything was operating well, and the DAF was probably the hardest thing to get operating well, we then had a study, basically a blind taste and odor study with city council members, PUC members. And what we found is basically, it's just about unanimous, that the GAC with permanganate made the best tasting and smelling water. Basically had no smell or taste. We sent in samples, all the MIB and geosmin were removed through absorption, and the microcystin, cyanotoxins were also removed. And since we were thinking we were going to have now a GAC, I'm going to call it GAC-BAC contactor, we're going to have our multi-barrier treatment for cyanotoxins and taste and odor compounds. What we did realize though through our analysis was that there was a lot of cell-bound taste and odor. So there's a microcystis bacteria right there, or algae I guess. And so we had to remove the cells. And what are the best possible ways for removing cells? Dissolved air flotation was one method, but since we decided that we were going to soften anyways, we found through literature and through some research that with a solids contact, well-operated solids contact clarifier, we were able to have about 95% of algae removal just through the clarifier, which is pretty much the same as the DAF system we found. So at that point where it was 200 parts of hardness, They could have decided not to soften. We would have went with DAF, but since we're softening, we went with the solids contact clarifier for algae removal. Conventional filtration, and we actually installed sodium permanganate instead of potassium just because they like dealing with that rather than the powder. Taste and odor control was the GAC BAC, and I'm calling it GAC BAC, which I'll talk a little bit more later, because obviously when you put it in there, it's acting as a contactor, it's absorbing, but our intent is to make it go biological and become BAC filters. Then chlorine contact chamber, ammonia, tie it up to monochloramines and send it into the distribution system. One thing I do want to note is that obviously the items that were causing the taste and odor were cyanobacteria, which only basically happen in the spring, June we'll have an event, and August, September we'll have an event, and a little bit in the summer. But winter months, we can bypass the GAC, BAC filters and the permanganate feed and all that stuff and go right from the conventional filters into our chlorine contact chamber if we want to. They did not do that this winter because the plant was just brought online and they didn't want to change the water quality for the residents while they were happy for it right then. Feeds, the coagulant is basically only fed when we have a algae bloom, when it hits us like a tidal wave. I saw Bill out there somewhere. Soda ash, they don't feed very often and haven't really needed to feed soda ash. Filter aid for surface plant ripening the filters, but so far the filter performance has been such that they really haven't had to use the filter aid and chlorine and ammonia. Science behind the treatment design. Why did we select these different treatment steps? Step one, basically settle out as much whole algae as possible. And we found that polymer is our friend. Like I said, algae doesn't want to sink, it doesn't want to settle, it wants to swim to the surface. So polymer is our friend. We found a polyacrylamide worked the best to tie the algae together, neutralize the charge, and be able to basically make long strings and settle it out. Step two, filter out as much algae carried over from the solids contact basins. Algae is very difficult, or cyanobacteria is very difficult to filter. It has a size of about 5 microns. So if you're going at enough velocity through your filters, it will actually carry through your filters and come out as turbidity. So that's one of the steps that we learned. So any algae that was carried through, we found our next step was to chop. I call this the Ginsu knife step, where we're using a hard or a strong oxidant to take that cell and lyse it, burst it. So at this step, we're actually trying to burst the cell because we're only carrying over about 5% of what we had before. So the reason we want to burst the cell, lyse, that's my own word for it, but lyse the cell is that those taste and odor causing compounds are inside the algae, much smaller, and at first we're able to absorb them onto the GAC. So absorption's occurring, taste and odor is occurring, removal is occurring, but once we have the BAC growth actually working well, doing what it's doing, we're creating assimilable organic carbon for that biological growth to basically eat and for a nutrient. Whereas if it was a whole cell, it wouldn't work as well. And this is a reason, that ozone is used quite a bit in the same step, and it works well for ozone quenching. BAC is one of the uses for ozone quenching. So this is our water treatment plant that we came up. This is actually a SCADA screen that we took from the plant. You can see that we have our 2 solids contact clarifiers, 2 recarb basins. These here, from there we go here to our conventional filters. Conventional filters, it actually drops down, comes over to an intermediate pumping basin. Since we have basically a hydraulic drop, we have to repump up to the GAC, BAC filters, which are the exact same size as the conventional filters, and then down into the chlorine contact chamber and into the clear well. Just real quickly, this is a public works garage, high surface pump room, and a chemical unloading facility. Construction phase. So this process took, I don't know, I think we started with a facility plan probably 6 years ago, something like that, maybe 7 years ago. We got into construction, and first step was digging the underground basins, excavation. For all of our underground basins, 50,000 cubic yards of material was excavated and removed from site. So right there we're about 28 to 30 feet down, and now they're working on the base slab. Pouring the base slab on this slide, you can see our they have the rebar set up for our chlorine contact chamber over our serpentine flow through our clear well, coming around and then into our pumping chambers. Here we're coming out of the subgrade level. Pouring the gallery level, you can see here we have a lot of pumps since we have a backwash pump, high service pumps, and then a dedicated one for future, and then also our intermediate pumps that will pump back up into the GAC contactors. It's hard to see there, but there's a lot of rebar that was going on in there, and just a lot of construction. Is pretty neat to see all this stuff. All the exterior of the plant was precast, so if you've ever worked with precast, it goes really, really fast. Here are in all basins inside the plant, all walls, well, all basins were cast in place with a Zypex compound that helped reduce any of the leaking that occurred and sealed that up. These here are the GAC filters with some of the pipe penetrations going through. These are the conventional filters that they're working on right now, or at that time. Right here I talked about we had a chemical unloading facility so they could offload lime, salt, chemicals, and that's where they also situated the semis for the dumping of their filter press. And I just had that out there. That is a 110-foot precast double T, or 105-foot actually, precast double T. They had to specially make those, and bringing it to site was pretty neat since it was so long. These back tires could actually articulate and turn around corners to get to site. And we are in the middle of Fairmont, right in the city, middle of a neighborhood. That's why we had that chemical loading facility to reduce the noise. Here they are flying in a 100-foot double T, setting into place. Filters. Basically, when we did the filters, we have two sets of filters I was talking about. The GAC filters, the conventional filters. They had to tremie in with a crane and the super sack, tremie in the gravel. Our conventional filters were 12 inches of rock, 12 inches of sand, and 18 inches of anthracite. The GAC filters had a media retaining cap and were 48 inches of GAC. And then for the anthracite and the GAC, they were able to use an e-ductor to pump all of that stuff in, so way less labor intensive for that. And then you can see the backwash troughs, the media retaining backwash troughs. Equipment, since we have lime trap, we pressed our lime. They had two 150 cubic foot filter presses. There they are flying one in. I believe they're like 65,000 pounds each. Dry, so as they're flying them in, getting set on site. The solids contact clarifiers, these are actually Westex solids contact clarifiers. This picture is before the hood, then once the hood is welded into place. The city went with stainless steel just to remove maintenance from the future for having to coat. The city, since we're in the middle of town, like I said before, the city decided to go with an on-site sodium hypochlorite generation system. We went with the Microcar System, and this is a salt, or the brine silo with salt in it. So basically, to generate our sodium hypochlorite, which is bleach, all it takes is brine solution and power, and we're getting a 0.8% sodium hypochlorite. With the 0.8%, since we're below the 1% threshold, we don't have to institute a risk management plan. So they got rid of that. We're safer because we don't have to deliver a ton cylinders into the middle of town. That was most of the reasons that we went with this system. Some statistics. We started construction in August of 2011. Pretty much about 25 months it took to get substantially complete, which happened on September 9th. They're still working on the demolition of the old water treatment plant. Final completion is in July of this year. And then we used 8,500 cubic yards of cast in place concrete. That doesn't include any of the precast concrete, and 800 tons of rebar. And just little caveats, there's lots of energy saving things went in there, motion sensing lights and solar tubes. And actually the solar tubes are quite impressive about how much light they put through there. So through research, and this is probably a lot of people would be interested in, there was no need for seeding. We talked to several utilities that already have biological filters, St. Paul being one of them, and other research that basically if you have the food source there, which in our case was MIB and geosmin, so we're promoting the growth of that bacteria that's going to take up the MIB and geosmin. Now if we had iron or manganese, ammonia, we'd be growing those kind of bacteria, but basically you provide the food, the bacteria is there, it's going to grow. Another thing was be mindful of the water quality and reclaim basin. And this is something we're still dealing with. So we're settling out 95% of the algae in our solids contact clarifier with our lime residual, so dropping to the bottom of the solids contact basin. Once it goes down through the blow off, it goes to the blowdown basin. From the blowdown basin, it goes to a lime solids holding basin. And from the lime solids holding basin, it goes to the filter presses. Well, all that water that's pressed out of the filter presses, by this time for sure all themselves have exploded because we just squished them with the filter press. All that water is full of MIB and geosmin and gets sent right to the reclaim basin. So we have a reclaim basin that at times could, I have no idea what the concentration would be, but plumb full of MIB and geosmin, taste and odor causing compounds. Now, we haven't had to deal with that because we started in September, so we're going to see what happens this next year. We're not sure if our bacteria on our BAC filters is going to be able to deal with it, or if we're going to have to just dump that water, because we do have the ability from the filter presses to send that water to sanitary sewer and not into the reclaim. This is one thing, conversion to GAC to BAC is synergistic. And the reason I say is synergistic is basically we put our GAC in there, we started up the plant, it took probably roughly a month to get all these pieces of equipment to work where we knew that we could probably send this out to the distribution system. So what happened is we were sending this out to the distribution system, and I think it was Burnsville said never start up a water treatment plant in the summer. Well, we did this, but we had the GAC as our safety blanket. So as this is happening, our GAC is absorbing all the taste and odor causing compounds, all this other stuff, and we're figuring that the GAC will probably be exhausted through research about 3 months. Also through some other research and consultation, we believe that in a good scenario in warm water, that the biological growth will establish itself in 2 months. So we have that overlap that we're absorbing taste and odor compounds, and then we're actually biologically taking them up. And before, we used to average 20 to 30 complaints per year at the old water treatment plant. Now they've had 1 complaint so far, and that was chlorine smell. So totally different than an earthy, musty smell. During startup, I think Bo had a reference this morning that an algae bloom can hit you like a tidal wave. Well, it did. We had a severe algae bloom about September 15th. We started the water treatment plant up at September 9th, feeding all this out to the distribution system. Got a call from the operator, basically said our clarifiers are completely green, and from blue to completely green, our filters are really green, and our turbidities are shooting up. What do we do? So basically kind of rushed over there, did a bunch of jar testing. And real quickly before the jar testing, thankfully we had our multi-barrier approach because our turbidities coming out, our combined effluent turbidity out of the conventional filters was getting 0.1, 0.2, 0.3, even a little bit higher than that. So we're getting way higher than we needed to be. But we had our second set of filters, our GAC filters, that the combined effluent turbidity out of them was still at that 0.1 range. So we're still able to meet that. Just give a plug to George Reck, I think he was here, and everybody in North Dakota, Minnesota, and South Dakota probably knows George. He came, did some jar tests, and we found this magic juice, the 4355 EHW, which is at a polyacrylamide polymer. And another thing that we don't have at this time, we're thinking about, there are inline raw water algae counters that we can use. So they would have some forewarning and get that batch polymer, it's a batch system too, to get that polymer up and running. And then just because it is startup and these things always happen during startup, they had a raw water ammonia spike. This happened in probably mid-October where they had 2 to 3 inches of rain. Their raw water ammonia went from 0.2 milligrams to 0.7 milligrams. Our original disinfection strategy is right before the conventional filters, we add about half a part of chlorine just to keep those filters from going biological. It gets all taken up and then go through the conventional filters, GAC filters where we don't want chlorine typically, and then into our chlorine contact chamber where we hit it for our CT and then are tied up with ammonia. But because of this, we weren't getting any chlorine basically into our chlorine contact chamber. So what we ended up doing is that we had enough CT through the plant that we totally shut off our ammonia feed, went and just used a natural ammonia, and we went to fed about, well, if you think about 4 or 5 parts, we were about 3.5 parts per filter, or per pre-conventional filter, so we went monochloramination right through the whole plant. Again, this would not be what we wanted to do if we had our BAC filters operating correctly, because we'd be probably stunting them if not killing them. But if we had our BAC in place, they would probably, or hopefully we'll have to see, be consuming this ammonia. So then we'd maybe go to our original treatment design, but that's something we'll have to figure out in the future. Performance measures, surface water plant, TOC removal. You can see they've always basically been meeting the TOC removal. Plant came online, TAC removal shot up. GAC absorption probably, and we're in cold weather months. But the line kind of came down, and we're going to be getting more data. And I'm really curious to see what the biological filters are going to do. I'm pretty confident that we're going to stay over here into our 60% TOC removal. Trihalomethanes, obviously we're moving TOC, everything. And they had problems with their trihalomethanes before. Just totally dropped to basically only 20 parts. And we're kind of going to hit that line again, see what happens in the summer. Similar results can be found for the HAA5. We didn't have a problem with them, but just went significantly down in concentration after the new treatment plant went online here in September. Okay, I was going to talk about the future of biofiltration, something I really love and really passionate about, and I think we're going to be seeing a lot more of that in the next 10 years, but I really don't have the time to talk about it. So I'll kind of just leave these slides up because Dave Schultz can attest to this. It's happening more than we know, and this is some of the data that we found at this. Why are they only adding 3.5 or 3.8 parts of chlorine when they have that much? And we found that their existing filters were biological, and they have this much coming in and 0.4 coming out of their filters and didn't know it. So with that, I guess I'll leave this up, and I can take any questions that anyone would have.
Did they have any nitrites coming off the filters?
Tested for that just a little bit, but no, they really didn't have a problem. Especially, I think we had enough DO that we were able to do the whole cycle, go from nitrate to nitrate. Anybody else? Okay.
All right, thank you, Jason.